it appears like it's its own lesson, but it's really not. It's kind of just a review of everything we've done. So there's going to be a bunch of situations. We're going to go through them really quick, and then the assignment should feel like a review. Okay, so the first situation is we're going to do speed versus step length. So we were talking about dogs. This person decided to research dogs for some strange reason and found an association between a dog's stride length. So stride length is like if you are walking, it's how far apart your feet are when you walk. So there's an association between a dog's stride length and its speed. The longer a dog steps, the faster it goes. Who would have thunk? Not this researcher, but that's what he found out. The predicted speed in meters per second, S, as a function of step length in meters L is blah. Okay? So I'm not a big fan of S and L, so I'm just going to rewrite this thing as y and x. Y equals 4x minus 1.6. Okay? So if I draw a quick sketch, y is the stride length. No, that's wrong. S is speed, not stride. So this is the speed the dog goes, and then this is the stride length. That's why I don't like S. All right? So if I draw a rough sketch of this, it looks like there's going to be a y-intercept of negative 1.6, and the slope is 4, so it's going to look something like this. Okay? So can a dog have a negative speed? No, really no. So this is kind of going to be like not useful data if we're talking about this scatter plot. So most likely what the data that this researcher took was like something like this. Okay? Maybe there's an outlier. Maybe there's other points. Yeah, it looks something like that. But I guarantee you it is not possible. There is no point down here because that literally does not make sense. The dog is traveling backwards in time? Like, I don't even understand. Okay? All right. So what does the rate of change of the function tell you about the association between stride length and speed? So this is a question that a lot of people had yesterday or 2 days ago. I forget which day this was when we were talking about slope, but this is the slope. So what does that slope of 4 tell you? Okay, so if I look at my actual line, let me get a different color. So if I go up 4, I go over 1. That's the definition of this situation's slope. Rise, up 4, over, run 1. Okay? So, let's see what this slope means for every... Now, we're going to do this as a unit rate. That's what a slope is, a unit rate. For every 1 meter of stride length, so for every 1 I go over in the x column, I go up how many? 4. A dog's speed increases by 4 meters per second. Okay, so that's what that slope would mean in this situation. Am I fully on screen? Yeah. Oh, yeah, I got tons of room. So that's what the slope means in this situation. Okay, and that's it for this. I just really wanted to recap about what speed meant, how you can interpret that slope using a real situation. My cats are still staring at the box of pens. This is interesting. Animal brains! Watch out, zombies. All right, so it's kind of hard to see here. Maybe I can zoom in. No, can't zoom in. Okay, so is there an association between the weight of an animal's body and the weight of an animal's brain? So I have an entire table of data there. If you click in on the slides on the detailed expectations, you can actually zoom in yourself. It'd probably be easier. I don't know if you can zoom in right now. Try it. Is there an association? Well, what do we think? Do you think that the heavier or the bigger an animal is, the bigger its brain is? I would say probably yeah. Let's see, what's the biggest land animal? An elephant? Do I think an elephant's brain weighs more than me? Or more than my brain? Yeah, probably. I would say probably just because elephants are huge. Have you seen the size of their head? There's probably a giant brain in there. Do I think that my brain weighs more than my cat's brain? Yeah. Okay, a cat's head is very small because they're small creatures, so their brain probably weighs less. That's what I would guess if I were to research this. Okay, so here is the graph. Do you think that there are any outliers in this data? Gee golly, that 1 point way up there, right up here. What animal that is? Let's see, so this is 100 kilograms, so then this would be 50 kilograms. So it's a little bit more than 50 kilograms. So let's look down our list, which is a little bit bigger than 50. Oh my gosh, it's human. That's right, humans are animals. So a human's body weight is 62 kilograms, and the brain weight is 1,320 grams. Okay, so yeah, I guess that makes perfect sense that a human is an outlier when we're talking about animal brains. Big shocker. This one over here kind of looks like an outlier too. What is this animal? That's like barely above 50. Oh, is it a sheep? No, it's not a sheep. Oh, it's a chimpanzee. Oh, another fellow member of the primate family has a big brain. That's interesting. Okay, now let's look down here. What is this animal? I feel really bad for this animal. This animal's kind of low. What is that? Like 190-ish? Let's look at 190. Donkey. Oh wait, donkey 187 and 419? Nope, donkey's up here. So it's like, it's not donkey. What else is close to 200, but under 200? Pig. Oh, poor pigs. Pigs have a body weight of 192 kilograms, and their brain weight is 180 grams. Oh, poor pig. This is like, which one is like really close to zero for both? Oh, that's cat. Wow, cats have really small brains. That's interesting. I thought cats were smarter. So let's think about that. What does it mean to be above the line? That means that your brain is larger than average. Okay, this line is an average line. Okay, if you're below the line, it means your brain is smaller than average. So cats are actually, they have smaller than average brains. Does brain weight equal intelligence? I don't really think that there's any science to back that up though. So even though cats on this list at least have the smallest brain compared to their body, I don't think that means that cats are the dumbest. And humans are the highest up there, but I do think that humans are obviously the smartest. But yeah, what are these super huge animals close to the right? Over 500. Giraffe, yeah. Do you think giraffes are significantly smarter than cats? No, I mean, they're probably similar levels of intellect. So just having a big brain doesn't make you smarter. Okay, so yeah, normally, so if you're doing data on animal brain weight versus body weight, you would probably not include humans, because if you include humans, Humans are like totally different, literally a completely different animal. So if you include humans, it's probably going to skew your data, and it's not going to make a whole lot of sense. So how do we, in general, determine a fitting line? Okay, so we haven't actually talked about how to make a line of best fit, but what we have done is been able to approximate. So the first step in finding a fitting line is to remove any outliers. That's step number one. You don't want humans on this graph because they're going to ruin everything. Step two is you get a straight edge, like we use spaghetti noodle, or I use spaghetti noodles. You get a straight edge, and you kind of just like keep wiggling it around until it looks like it's the right amount. So it looks like this spaghetti noodle goes pretty much through the center of everything. Okay, so here is a new situation. Let's assume that we want to find out how much a T-Rex's brain weighed. Okay, so a T-Rex, we are estimating, obviously no one's seen a T-Rex, we are estimating that a T-Rex weighed 8,000 kilograms. What would you expect its brain weight to be? Okay, so what I would do is I would find something that's really close to or divisible, that something I can divide 8,000 by. So I think 400, let's see, if I do 8,000 kilograms and I want to compare it to 400 kilograms, that would be a really nice comparison to make, because I know 8,000 divided by 400, that's like 20. That's like a 20-to-1 ratio. Okay, so I'm going to look on my graph, where is this 400 kilogram line? 400 kilograms, okay? So I'm just gonna try to draw a rough sketch of what I see there. And if I go over to 400, where is this? Okay, so this is an animal that is 1/20th the size of a T-Rex. Okay, so if I go to 400, it looks like it's at almost exactly 500. So it looks like it's about 500. And remember, our brain weight is in grams. Okay? So if a 400 kilogram creature is estimated to have a brain weight of 500 grams, what is an 8,000 kilogram creature going to have a brain weight of? So what we're going to do is we are going to create a proportion. This 400 kilogram creature has a brain weight of 500. What is the brain weight of the T-Rex? So I set up a proportion. Big animal to little animal, big animal to little animal. How do we solve proportions? We cross multiply and divide. Actually, we don't have to cross multiply here. I see it's x divided by 500. So one thing I'm going to do is I'm just going to multiply both sides by 500. And it cancels that out completely. And now I just have x all alone. So if I type this in on my calculator, let's figure out what my brain weight is going to be. 500 grams times 8,000 divided by 400. 10,000. And my units would be grams. So 10,000 grams was that 10 kilograms. So a T-Rex's brain is about 10,000 grams. Actually, that seems kind of like a small brain compared to humans. I guess that makes sense. This is called an extrapolation. And extrapolation is when you use a trend outside its measured data set. So if we look back at our actual scatter plot, did we measure any animals close to 8,000 kilograms? No, our heaviest animal measured was what, like 520, something like that, it looks like 520. So we measured an animal way outside our data range. Okay, so oftentimes these extrapolations are not reliable. Okay. However, if I were to look at this data set and say how much or what is the brain size of a 300 kilogram animal, you would probably be able to reasonably assume that because we have some animals that are less than 300 and some animals that are more than 300. So we would be finding a new point in the middle of our data versus this is a point. So like here's our graph. This T-Rex is like, oh, way, way out there. So it's probably not going to be reliable at this point. So that's called an extrapolation. Okay, last situation of the day. Imagine we are going to take data on our arm span versus our height. So you get a tape measure. You measure how long it's like wingspan for birds. So you measure your wingspan or your arm span, and then you measure how tall you are. Okay, so you're taking those two measurements. One of them's X, one of them's Y. Boom. Here's all the data. I just measured every single one of you and plotted the data instantly because I'm a time traveler. Okay, so let's take a look at this data. What would be a reasonable slope, do we think? So let's look at our X and Y axis labels. And I know it's probably really hard to see, but if you actually get close and like you analyze this data, let me look. So I see 150. 150 arm span is about 154 height. 160 arm span is about 162 height. 170 arm span is about 170 height. 180 arm span is about 179 height. So it looks like your arm span is just about exactly the same as your height. Just about, okay? So that's not 100%. Obviously, it's a scatter plot. So our equation is going to be y equals 1x. They are about the same. So y is pretty much the same as x. Okay? So, what does it mean if you are above this line, and what does it mean if you're below? Let's take a look at that graph. So all these dots that are above, let's see, the y-axis represents your height. So if you are above this line, it means that your height is bigger than your arm span. If you are below the line, that means your height is smaller than your arm span. Okay? When I was in high school, some people that I called friends called me monkey arms because I had really long arms for my height. So that would mean I was short and had long arms. So me personally in high school, my dot would have been below the line. I haven't measured myself since, so I don't know if that's still true. But that is one thing that my so-called friends called me in high school. All right. Okay, so let's say you actually do this for everyone in your neighborhood or your subdivision or even the entire town. Okay, let's say you take this data and we have person's height and we have arm span here. And let's say all of our data, it looks like we've got a bunch of data like this, and we've got a bunch of data like this. And of course, there's a little bit of data in the middle, but most of the data is down here, and most of the data is up here. So we have two clusters of data. Okay? What does that mean? Well, let's take a look at this cluster right here. All of this data is people that are short and have a small arm span. What do you think that is? Probably kids, like under, let's say under 13. okay? Maybe even under 10, okay? Really, really small kids. And then we have all of this data up here. What do we think those are? Well, those are probably adults. Okay? We also have just random assortment of dots in the middle. Those are probably adolescents who are currently going through puberty, or maybe just adults that are shorter than average, or maybe something else. Okay? So, what does a point in a scatter plot tell you? It tells you two specific measurements about an individual in a population. So in this scenario, it tells you about their arm span, and it tells you about their height. What is an association between variables? It means that if there's a trend, it means that as one increases, the other one does something predictably. If you know one piece of data, you can find the other one through math. What does a fitted line tell you about the data? It represents a model that can be used to make predictions about the dependent variable based on the value of the independent variable. Holy moly, that's a mouthful. Let me reread that. So the fitted line tells you kind of like a general rule. So you can use that general rule to find missing information. What does the slope tells you? The slope tells you at what rate the two variables are connected, increasing or decreasing. And that's it for today. Yay! If you have any questions, feel free to let me know. This is our last lesson on scatterplots. Pretty exciting. How do I stop this recording? I always forget.